All right, today we're diving into one of the oldest, most heated debates in all of computing. And we're going to see how a long-held assumption, something everyone just took for granted, is being completely overturned. We're talking about the kernel, the very heart of your operating system.
Okay, so for decades, you basically had two camps in the operating system world. First, you've got the monolithic kernel, like Linux. Think of it as a giant all-in-one skyscraper. Everything's in one building, super optimized for speed. Then you've got the challenger, the microkernel. This is more like a modular city campus, lots of smaller, separate buildings. It's way more secure and flexible, but it's always had this one giant problem, a performance tax. Basically, it's the time it costs for all those separate buildings to talk to each other. And that tax has always been way too high.
For the longest time, that monolithic skyscraper was the undisputed champion of performance, no question. But the world changed. The hardware underneath our software started to look completely different. And that skyscraper design, well, it started hitting a wall, a very, very hard wall.
Yeah, we're talking about the explosion of multi-core processors. We're building chips now with 64 cores, 128 cores, and we're not stopping there. And it turns out the very all-in-one design that made monolithic kernels so fast with a few cores becomes a massive, crippling bottleneck when you have dozens of them.
So what's actually happening here? Well, on these big multi-core systems, all the cores inside that single monolithic skyscraper start tripping over each other. They end up in a traffic jam, waiting to get access to the same shared data. That's called lock contention. Data starts bouncing back and forth between them like a ping pong ball, and the whole system grinds to a halt. Performance doesn't just level off, it actually gets worse the more cores you add. So, a new generation of computer scientists looked at this problem and had a wild idea. To finally beat the monolithic kernel, you couldn't just try to minimize the microkernel's weaknesses. No, you had to flip the script entirely. You had to turn those weaknesses into strengths by totally rethinking how software should talk to modern hardware.
And this is that master plan. First, tear down the walls between different parts of the OS and run everything in one big, open space. Second, get rid of the traffic jams by treating all the CPU cores like a network, having them pass messages instead of fighting. Third, and this is huge, stop copying data. Instead, just pass around secure keys to it. And finally, let the hardware talk directly to its drivers, cutting the kernel out of the conversation.
Now you might be thinking, that sounds great in a lab, but can it actually work in the real world? And the answer is yes, absolutely. But it's not just a software trick. The real hero of this story, the missing piece of the puzzle, finally arrived in the form of new hardware.
The key technology here is called capability hardware. Okay, imagine this. Instead of one security guard at the front door of your building, you put a tiny, super fast security guard on every single bit of memory. Every pointer now comes with its own set of permissions, and it's all enforced by the silicon itself at the speed of electricity. Suddenly, the isolation that used to be slow becomes practically free.
And that really leads to this quote, which just nails it. The whole microkernel philosophy, the city campus idea, it was never wrong. It was just way, way ahead of its time. It was an idea literally waiting for the hardware to catch up. To really feel the impact here, let's look at how data used to get around. In the old monolithic world, the kernel was like this overworked mailroom clerk. It had to go grab the data from, say, a network card, copy it all into its own secure room, and then copy it all over again to hand it to your application. All that copying is just wasted time and energy. Now the new way completely demolishes that bottleneck. The kernel isn't a mailroom clerk anymore. It's more like a traffic controller. It doesn't move the data at all. It just instantly hands your application a hardware-enforced key, that capability we were talking about, and says, here, you have permission to access the data right where it is. The ownership transfer happens in a single CPU cycle. That is zero-copy I/O, and it is an absolute game changer.
So what happens when you combine this visionary software blueprint with this revolutionary new hardware? Well, you get what we're calling the great performance flip. The entire equation just turns completely on its head.
I mean, just look at this chart. That infamous performance tax that killed microkernels for a generation, it's gone. Poof, vanished. Communicating between two isolated programs used to cost thousands of CPU cycles. Now, it's down to a few dozen. It's almost as fast as a direct, unprotected function call inside a monolithic kernel.
Let that sink in. Around 28 cycles for a fully secure, hardware-protected communication between two separate programs. The fundamental trade-off between security and speed, a rule that has defined system design for 50 years, has just been broken.
And this is exactly why it matters on modern machines. The monolithic kernel is fighting a losing battle against the physics of multi-core chips. It hits a wall. But this new microkernel architecture is designed from the ground up to exploit that physics. Its performance doesn't just get a little better with more cores, it scales almost perfectly in a straight line.
Look, this isn't just some academic victory. This has profound, real-world implications for the stability, the security, and the performance of pretty much all the software we're going to use in the future.
We're talking about a future with self-healing systems, a future where a buggy video driver crashes and it just instantly restarts itself with zero system downtime. You wouldn't even notice. A future where critical parts of the OS can be updated live without ever needing a reboot. And a future where our apps can finally, efficiently, take full advantage of the hundreds or even thousands of cores that are coming our way.
So the real takeaway here is that a foundational assumption of computing, the idea that security and modularity must come at the cost of performance, has been completely shattered. And that leaves us with a really fascinating question to think about. If a simple driver crash could never take down your whole system ever again, what entirely new kinds of software would we start to build?